Cottbus, Germany, January 1945. Kurt Tank stood beside his latest creation as ground crew completed final preparations. The Ta-152H-1 gleamed in the weak winter sunlight, a fighter designed for one specific purpose: to reach altitudes where no other piston-engine fighter could operate effectively. Tank had spent 3 years developing this aircraft, 3 years solving problems that seemed impossible to solve. But on this January afternoon, he faced a more immediate concern: proving his aircraft could actually do what he'd promised. The stakes weren't theoretical. Allied bombers now operated at altitudes that made interception nearly impossible. German fighters gasped for air at 40,000 feet, while B-29s droned overhead. Untouchable Tank's solution sat before him. If it worked. He had approximately 90 minutes of daylight remaining to discover whether 3 years of his life had produced a weapon or a failure. By January 1945, altitude had become Germany's most critical tactical weakness. The numbers told a brutal story. American B-17s operated comfortably at 25,000 feet. British Lancasters struck at 22,000 feet. Standard German fighters, the Bf-109G and FW-190A, could reach these altitudes, but barely. At 25,000 feet, a Bf-109G6 took 17 minutes to climb from sea level. It arrived with engine temperature redlined, pilot oxygen-starved, and combat effectiveness reduced by approximately 40%. German pilots called it the altitude trap. Climb to intercept, and you arrived too exhausted to fight effectively. Stay lower, and bombers passed overhead untouched. Then came the B-29 Superfortress deployment rumors from the Pacific. Intelligence reports indicated operational ceiling above 38,000 feet. If these aircraft reached European skies, existing German fighters would be completely obsolete, unable even to reach engagement altitude. Tank had recognized this problem in 1942. As chief designer at Focke-Wulf, he understood piston engine limitations. Above 20,000 feet, atmospheric pressure drops precipitously. Engines lose power. Propeller efficiency plummets. Aircraft that dominated at low altitude became sluggish, vulnerable targets in the thin air above 30,000 feet. The Luftwaffe had attempted solutions. Emergency power system boosted performance temporarily, at the cost of engine life measured in minutes rather than hours. Pressurized cockpits helped pilot performance, but added weight. Larger superchargers increased high-altitude power, but reduced low-altitude effectiveness. Each solution created new problems. Higher compression ratios required higher octane fuel. Fuel Germany couldn't produce in sufficient quantities. Larger engines meant heavier airframes. Heavier airframes meant reduced climb rates. The engineering problems formed an interconnected web. Tank's approach differed fundamentally from previous attempts. Rather than modifying existing designs, he started from first principles. Design an aircraft specifically for high-altitude interception. Accept compromises at low altitude to achieve dominance at 40,000 feet. The Ta-152H incorporated solutions that seemed contradictory. Wingspan extended to 14.4 meters, nearly 2 meters longer than standard FW-190. Longer wings generated more lift in thin air, but reduced roll rate and increased weight. Tank accepted this trade-off. He specified a Junkers Jumo 213E engine with 3-stage supercharger. The supercharger system alone weighed 285 kilograms. It consumed power at low altitude, but at 40,000 feet, it would deliver 1,750 horsepower, while competitors' engines produced barely 800 horsepower. The pressurized cockpit added 150 kilograms. The MW-50 water methanol injection system added 85 kilograms. Extended fuselage for balance added structural weight. The TA-152H-1 weighed 4,730 kilograms fully loaded, nearly 800 kilograms heavier than a FW-190A8. Critics within the Luftwaffe called it a compromise aircraft. Too heavy for low-altitude dogfighting, too specialized for general fighter duties. Tank disagreed. At 40,000 feet, compromises became advantages. But theory required validation. The Ta-152 had flown test flights at moderate altitudes. Performance below 30,000 feet seemed acceptable, not exceptional, but adequate. The critical question remained unanswered. Could it actually dominate at the extreme altitudes for which Tank had designed it? Production facilities at Cottbus had completed 34 airframes by mid-January. Luftwaffe leadership demanded immediate deployment. Tank insisted on comprehensive high-altitude testing first. The disagreement reached Göring's office. The compromise: Tank personally would conduct one definitive high-altitude test flight. If results proved promising, immediate operational deployment. If not, production cancellation. January 22nd became decision day. Tank would climb to maximum altitude, somewhere above 40,000 feet if the aircraft performed as designed, and determine whether 3 years of engineering had produced the weapon Germany desperately needed. Tank had test-flown hundreds of aircraft during his career. But this flight felt different. He understood the broader implications. If the Ta-152H1 failed to perform at altitude, Germany lost its only potential answer to high-altitude bombing. Production resources would shift to jet fighters. Aircraft that required fuel, Germany increasingly couldn't provide, and runways that Allied bombing systematically destroyed. At 14:47 hours, Tank climbed into the cockpit. The pre-flight checklist took 12 minutes. Fuel system: pressurized for high-altitude operation. Oxygen supply: 90 minutes at maximum flow. MW-50 tank, filled for emergency power. Cockpit pressure system, tested to 8,000-meter equivalent. Ground crew chief reported external checks complete. Tank started the Jumo 213E. The engine caught immediately, 3-stage supercharger whining distinctly different from standard fighters. At idle, the Ta-152 sounded like it belonged at altitude. 15:03 hours, takeoff clearance received. Tank advanced throttle. The Ta-152 accelerated slowly. That 4,730 kilogram weight evident immediately. Standard FW-190A8 typically lifted off after 450 meters. Tank's aircraft required 620 meters. The long wings generated lift reluctantly in ground effect. Gear retraction at 180 kilometers per hour. Initial climb rate, 840 meters per minute. Tank noted the figure with satisfaction. At sea level, the TA-152 climbed slower than BF-109G or FW-190A. This was expected. The aircraft wasn't designed for sea-level performance. He climbed in a wide spiral, carefully monitoring engine parameters. Cylinder head temperature remained well within limits. Manifold pressure stable. The Jumo 213E ran smoothly. No indication of the valve problems that had plagued earlier test aircraft. At 5,000 meters, 16,400 feet, Tank engaged the second supercharger stage. Engine note changed slightly. Power output increased. Climb rate improved to 920 meters per minute. The Ta-152 was entering its element. At 8,000 meters, 26,000 feet, Tank activated cockpit pressurization. Pressure differential gauge showed steady climb toward 8 psi, equivalent to maintaining sea-level pressure inside the cockpit. His breathing remained normal. No oxygen deprivation symptoms, no pressure discomfort. Standard fighters at this altitude made pilots feel half dead. Tank felt perfectly alert. But the critical test lay ahead. He continued climbing. 9,000 meters, 29,500 feet. Climb rate still 780 meters per minute. At this altitude, BF-109 G6 climb rate dropped to approximately 450 meters per minute. The Ta-152 was pulling ahead of its competitors. 10,000 meters, 32,800 feet. Manifold pressure still solid. Engine temperature stable. Climb rate 680 meters per minute. Tank noted contrails forming behind his aircraft. Visibility extended for hundreds of kilometers in the crystal-clear winter air. He could see Berlin to the northwest, columns of smoke rising from recent RAF bombing. To the east, the front lay approximately 200 kilometers distant. Red Army artillery could be heard on clear nights now. 11,000 meters, 36,000 feet. Third supercharger stage engaged automatically. Brief power surge. Climb rate stabilized at 580 meters per minute. This was the altitude where theory met reality. Tank leveled briefly, checking aircraft response. Control surfaces remained crisp. No mushiness. No warning signs of impending stall. He pushed throttle to climb power again. 12,000 meters, 39,300 feet. Climb rate, 420 meters per minute. Airspeed, 450 kilometers per hour indicated. The altimeter continued winding upward. Tank watched it with growing realization. The TR-152 wasn't struggling. At an altitude where BF-109G pilots fought simply to maintain level flight, his aircraft climbed comfortably. At 12,500 meters, 41,000 feet, Tank leveled off. He paused, absorbing the moment. Outside temperature, minus 56 degrees Celsius. Cabin temperature, plus 18 degrees Celsius. Oxygen flow, normal engine parameters, all normal, no vibration, no roughness. The TR-152 operated at 41,000 feet as smoothly as most fighters operated at 15,000 feet. Tank initiated handling tests. Roll left, response immediate, precise. Roll right, equally responsive. Pitch up, clean brake, no stall warning. Pitch down, acceleration smooth. He attempted a combat turn. At 41,000 feet, most fighters developed uncontrollable stalls when banking more than 30 degrees. Tank rolled into 45-degree bank, pulled back on stick. The TR-152 turned. No buffeting, no stall warning, just smooth, controlled maneuvering. Then came the critical test. Acceleration at altitude. Tank pushed throttle to full power and engaged MW50 injection. The methanol water mixture sprayed into the supercharger intake, cooling compressed air and allowing temporary overboost engine note deepened. Manifold pressure spiked to emergency level. The TR-152 accelerated. At 41,000 feet, airspeed increased from 450 kilometers per hour to 510 kilometers per hour, then 540 kilometers per hour. At 560 kilometers per hour, indicated airspeed, approximately 740 kilometers per hour, true airspeed accounting for thin atmosphere. Tank eased throttle back to normal combat power. He had just achieved 460 miles per hour at 41,000 feet in a piston engine aircraft. For comparison, P-51D Mustang maximum speed at 40,000 feet was approximately 395 miles per hour. Spitfire 14, roughly 380 miles per hour. BF-109, G-6, barely 340 miles per hour. The TE-152H1 was 65 miles per hour, faster than its closest competitor at extreme altitude. And it maneuvered better. And its pilot remained alert and effective, while competitor pilots gasped for oxygen and fought control sluggishness. Tank initiated descent. Mind processing implications. Every high-altitude interception problem Germany faced suddenly had a solution. B-29s operating at 38,000 feet. The TA-152 climbed above them, dived through formations with speed advantage, high-altitude photo reconnaissance aircraft. The TA-152 caught them. Bomber formations escorted by P-51s. The TA-152 engaged at altitudes where Mustangs lost effectiveness. But descending through 8,000 meters, landing gear extending at 3,000 meters, Tank confronted the other side of his success. Timing. The TR-152H1 proved that German engineering could still solve impossible problems. But wars aren't won by engineering excellence. They're won by production capacity, logistics systems, and strategic resources. And by January 1945, Germany had lost all three battles. The TR-152H1 represented 3 years of focused engineering, solving problems that most designers considered unsolvable compromises. Tank's central insight, altitude performance required accepting low-altitude disadvantages. This contradicted standard Luftwaffe doctrine, which demanded fighters capable of engaging across all altitudes. Tank ignored doctrine and optimized ruthlessly for one mission: high-altitude interception. Wing design exemplified this approach. The 14.4-meter wingspan created lift coefficient ideal for thin air at 40,000 feet. But that same wingspan increased roll inertia, making rapid directional changes more difficult at low-altitude. Tank accepted this. At 40,000 feet, the aircraft would fight opponents equally sluggish. At low altitude, it would avoid combat. Wing loading, aircraft weight divided by wing area, measured 219 kilograms per square meter. This was relatively low compared to late war fighters. Lower wing loading meant better high-altitude maneuverability but reduced maximum dive speed. Again, Tank accepted the compromise. High-altitude interception required turning ability, not maximum dive speed. The Jumo 213E engine provided the critical advantage. Its three-stage supercharger system consumed 285 kilograms of weight and approximately 12% of engine power at sea level, but it compressed air sufficiently to maintain combustion efficiency at extreme altitude. Supercharger physics explained the advantage. At sea level, atmospheric pressure measures approximately 14.7 pounds per square inch. At 40,000 feet, atmospheric pressure drops to 2.72 psi. Barely 18% of sea level pressure piston engines require specific air-fuel mixture ratios. Less air means less fuel combustion, which means less power. Superchargers compress intake air, restoring pressure before combustion. Single-stage superchargers restore some pressure. Two-stage superchargers restore more. The Jumo 213E's three-stage system restored sufficient pressure at 40,000 feet to maintain approximately 1,750 horsepower, more than double what single-stage engines produced at that altitude. The MW50 injection system provided emergency power increase. Methanol-water mixture 50-50 ratio sprayed into supercharger intake cooled compressed air. Cooler air increased density. Denser air allowed more fuel combustion without detonation. Result: temporary 25% power increase. MW50 consumption measured 115 liters per hour at full injection rate. Tank capacity, 70 liters. Maximum injection duration, approximately 37 minutes. This limitation meant careful tactical planning. Emergency power reserved for critical engagement moments. Pressurized cockpit solved physiological problems. At 40,000 feet without pressurization, human consciousness deteriorates rapidly. Oxygen provides breathable gas, but doesn't solve pressure differential problems. Blood nitrogen bubbles form. Mental clarity degrades. Physical coordination suffers. The Ta-152's pressure system maintained cabin equivalent to 8,000 meters, even when aircraft operated at 12,500 meters. This kept pilot fully alert and effective. Competitor aircraft pilots at 40,000 feet fought through cognitive impairment, even with oxygen masks. Fuel system incorporated high-pressure pumps to ensure engine feed at extreme altitude where standard gravity-fed systems failed. C3 fuel, 96-octane equivalent, enabled high compression ratios without detonation fuel capacity. 595 liters internal, plus optional 300-liter drop tank. Range at cruise power, approximately 2,100 kilometers, sufficient for deep penetration escort interception. Armament configuration emphasized bomber destruction over fighter combat. 1 Mk 108 30mm cannon firing through propeller hub delivered 360 rounds. 2 Mg 151/2 020mm cannons in wing roots provided 350 rounds per gun. The 30mm cannon could destroy heavy bomber with 4 to 6 hits. This firepower emphasis reflected tactical priorities. Reach altitude, destroy bombers, return to base. Aircraft weight distribution required careful engineering. Long nose, housing Jumo 213E, created forward center of gravity. Extended rear fuselage balanced this result. Neutral stability that made aircraft responsive at altitude without becoming unstable at high speed. Landing gear retraction system used hydraulic pressure rather than standard pneumatic. Hydraulic fluid remained effective at extreme temperatures, both minus 56 degrees Celsius at altitude and plus 40 degrees Celsius during emergency power operation. Pneumatic systems froze at extreme altitude. Production methodology reflected war economy pressures. TA-152H1 required approximately 9,500 man-hours to produce, substantially more than BF-109G, 5,000 hours, or FW-190A, 6,000 hours. Complex supercharger installation, pressurization system, and extended airframe increased labor requirements. Material requirements also exceeded standard fighters. High-strength aluminum alloy for pressurized cockpit. Special seals for pressurization. Three-stage supercharger components. Each system required materials Germany increasingly struggled to source. But tanks engineering proved effective. The Te-152H1 solved every technical problem associated with extreme altitude operation. At 41,000 feet, it outperformed every piston engine fighter built by any nation during World War II. The question wasn't technical capability, the question was timing. Tank landed at 16:34 hours. Total flight time, 91 minutes. Ground crew surrounded the aircraft immediately. Tank remained in cockpit briefly, completing shutdown checklist. Engine temperatures normal. No anomalies. The TA-152H1 had performed flawlessly. Luftwaffe observers wanted immediate debriefing. Tank's report was concise. The aircraft exceeds design specifications at extreme altitude. It provides clear superiority over any known opponent above 35,000 feet. He recommended immediate operational deployment, but reality intervened in the form of production capacity and strategic timing. Cottbus facilities could produce approximately 12 Te-152H1 aircraft per month. By comparison, American factories produced roughly 1,400 fighters monthly in January 1945. Even if Ta-152 production reached maximum efficiency, Germany would deploy perhaps 150 high-altitude fighters before war's end. Allied bombing had already destroyed or damaged primary Junkers engine production facilities. Jumo 213E availability would limit production regardless of airframe manufacturing rate. Tank had designed a superior aircraft. German industry couldn't produce it in relevant quantities. Fuel logistics created additional constraints. C3 high-octane fuel required for Jumo 213E operation was increasingly unavailable. Synthetic fuel plants faced systematic bombing. Remaining stockpiles prioritized jet fighter operations. Me-262 and R-234 received fuel allocation before piston fighters. Operational deployment revealed the timing problem more clearly. JG-301 received first operational Ta-152H1 aircraft in late January 1945. Pilots reported aircraft performance as exceptional at altitude. They also reported that Allied bomber formations now operated with massive fighter escort, P-51Ds, numbering 50 to 100 aircraft per bomber group. Even superior individual aircraft performance couldn't overcome numerical disadvantage. A Ta-152 could outfight any P-51D at 40,000 feet. But facing 10 P-51s simultaneously, superior performance became irrelevant. By March 1945, the Eastern Front had collapsed to within 60 kilometers of Berlin. Cottbus airfield came under Soviet artillery range. Production facility evacuation began. In total confusion, workers dismantled tooling, loaded equipment, attempted relocation to Bavarian facilities. Approximately 150 Ta-152H1 aircraft had been produced by April 1945. Of these, perhaps 40 reached operational units with trained pilots. Combat effectiveness reports indicated favorable kill ratios. Ta-152 pilots claimed 13 confirmed victories for 2 losses in air combat during March-April 1945. But 13 victories against thousands of Allied sorties meant statistical irrelevance. The TR-152 demonstrated conclusively that German engineering could solve extreme altitude problems. Tank had designed precisely the aircraft needed to counter B-29 deployment and high-altitude bomber tactics. His solutions worked. They worked 3 years too late. In 1942, when Tank initiated TI-152 development, Germany held strategic advantage. Resources existed for long-term development programs. Production facilities operated without systematic bombing interference. Fuel supplies remained adequate. Pilot training produced skilled replacements. By 1945, when the TA-152H1 proved its superiority, strategic situation had transformed completely. Resources couldn't support specialized aircraft production. Allied air superiority prevented effective operations regardless of aircraft performance. Fuel scarcity grounded even available aircraft. Post-war analysis by Allied technical intelligence teams confirmed Tank's engineering success. One American test pilot noted, "At 40,000 feet, this aircraft handles better than most fighters handle at 20,000 feet." If Germany had deployed this in meaningful numbers 2 years earlier, high-altitude bomber operations would have required fundamental tactical revision. The number comparison told the story most clearly. Tank's Ta-152 could outperform any Allied fighter at extreme altitude, but Germany produced 150 total Ta-152s during 1945. America produced 21,000 fighters during the same period. Engineering excellence divided by 140 to 1 production ratio equals strategic irrelevance. The TA-152H1 became military history's clearest demonstration that technical excellence cannot overcome strategic disadvantage. Tank had created the right weapon, but weapons require production capacity, logistics support, trained personnel, and strategic time frame for deployment. Germany lacked all of these by January 1945. Tank survived the war and continued aircraft design career in Argentina and later India. He later reflected that the TA-152 represented both his greatest engineering achievement and his most frustrating professional experience, proving conclusively that brilliant solutions to military problems mean nothing if they arrive after strategic context has already been decided. The Ta-152H1 demonstrated altitude supremacy during its 90-minute test flight on January 22, 1945. But altitude supremacy in 1945 was solving a problem from 1942's battlefield wars move faster than engineering development cycles. And when they do, even perfect technical solutions become historical footnotes documenting what might have been, if only timing had aligned differently. Tank's test flight proved German engineering could still achieve technical miracles. But it also proved something more important: that wars are won by factories, supply chains, and industrial systems, not by individual acts of engineering brilliance, no matter how remarkable those acts might be.